In this video, we are going through 10 MCQ questions from pure to science physics from various years related to the concept on factors that affect the resistance of a conductor. If you have watched the previous video, so when the length increases, your resistance will increase. When your cross-sectional area increases, your resistance will decrease. And lastly, your resistivity of the conductor increases, your resistance will increase. So this two is direct proportion and the cross-sectional area is inverse. That's why you have this formula. All right. But if you can see, all you need is actually just these two because most of the question is all using the same material. So resistivity will be constant. So let's start with the first question. So which of the following changes to the wire doubles its resistance? So let's assume the original resistance is R. Okay, so for the new resistance here, let's say the new one, I'll start with the original R and let's look at the factors one by one. Let's start with the cross-sectional area. As you know, if the cross-sectional area is higher, the resistance will be lower. So if the cross-sectional area doubles, the resistance has to be smaller. So I divide by 2 or times half if you want to. And now let's take a look at the length. If the length is double, it's longer, the resistance should increase, should double. So times 2, and you end up with the resistance R, which is the same as the original. So it is not double, so that's not the answer. So let's do the second one. Starting with the original R, and the cross-sectional area doubles, resistance will be half, and the length no change, that's all. So the final R for this new one will be R over 2, which is not what I want. Let's start with the half. So the new resistance, because the cross-sectional area is half, so it's thinner, so therefore the resistance will be double. So it's R times 2, make it bigger. And then when the length is half, the resistance will be half also. So times half, you end up with R. So that's not what I want. And let's take a look at the final one. R times 2, and there's no change, so you have a final resistance of 2R, which is what I want. So the answer will be D. In this question, we have a wire of resistance 8 ohms, and we have a second wire of the same material, so resistivity will be the same, and this new wire has half the length and twice the cross-sectional area. That means to say this is, if this is L and A, this will be L over 2, and this is 2A. So the resistance of the second wire, as mentioned, we will start with the original resistance of the first wire. Now let's consider the length. Because the length is shorter, half, the resistance will be smaller, half also. So divide by 2, and the cross-sectional area is 2 times bigger, it's thicker now. Resistance should drop and reduce by half. So divide by 2, therefore you will get 2 ohms. So B will be the answer. Next question, similar to the previous one, you have a resistance that is 80 ohms, that's your P, and you have Q, another wire which is of the same material, same resistivity. The cross-sectional area of Q is 4 times, so it's 4A, and the length of Q is 2L, twice the length. So the new resistance for the Q will be using the original resistance 80 ohms, and because of its cross-sectional area that increases by 4 times, the resistance should reduce by 4 times. So divide by 4, and then let's consider the length is double, so resistance will double times 2. So effectively the total resistance will be 40 ohms. So the answer will be B. Next question, a bit similar, but the only difference is they give you the values instead of telling you the cross-sectional area increases by how much. So let's take a look at the first one. It's 2 meters long, and the cross-sectional area is as such, and the original resistance is 1.2 ohms. Then you have another wire of the same material, same resistivity, but the length is now 0.5 meter, and cross-sectional area is 1 times 10 to the power minus 6. Now, if you pay attention, let's consider the length. So from 2 meters, it goes down to 0.5 meters. So there's a reduction. So it becomes shorter by 4 times. Okay, so let's start with the new wire. All right, So, and the original resistance 1.2 ohms as mentioned, because the length reduces from L to L over 4, so the resistance will be reduced by 4 times, so divided by 4. And now let's consider the cross-sectional area. So from 0.5 times 10 to the power of 6 minus 6 to 1.0, so basically the area is double. So if the area is double, increases, thicker, the resistance should decrease and is half, so divided by 2. So the answer is 0.15 ohms. So answer is A. Now maybe for this question, some of you might ask, can I use the formula that you learned, R equals to rho L over A? Well, if you want, can also, because the two wires are made of the same material, so the resistivity of the wire A will be the same as resistivity of the wire 2. So if you rearrange here, rho equals to R A over L. So in other words, the resistance of 1 times the area of 1 or length of 1 equals to resistance of 2, which is the unknown that you want to find, and the cross-sectional area of the wire 2 times the length of wire 2. So basically you just sub in the value and just to find the unknown R2. You can use the formula if you want to, but I think it's a bit more tedious actually, so up to you. This question very almost identical to the previous one. So a wire of length 0.5 meter, cross-sectional area of 1 times 10 to the power minus 6 has a resistance of 0.75. Another wire, same material, which is 2.0 meters now, is longer by 4 times, and the cross-sectional area is 0.5 times 10 to the power minus 6. So the area actually half. So let's start with the new wire, and then let's use the original resistance 0.5. Let's consider the length. From L, it becomes, okay, so from 0.5 to 2 meters, basically it increases by 4 times. So it's become 4 over L 4 times. Or you take 2 divided by 0.5, that's an increase by 4 times. So the resistance will definitely increase and increase by 4 times 4. Next, the cross-sectional area from 1.0 and times 10 to the power of minus 6 is the same. So from 1.0 to 0.5, actually the cross-sectional area is half, thinner, so resistance should go up and it will double, so times 2. So the answer will be 6.0 ohms, so it's D. So in this question, you have a resistor of original resistance R and the length is L with a cross-sectional A. Second wire with a resistor of 2R is made of wire of the same material, same resistivity, and the cross-sectional area is A over 4. So this is thinner and thinner by 4 times. So what is the length? So as mentioned, you can also use the same techniques. The second wire, all right, so let's start with the original wire, and the only information we have is the cross-sectional area. Since it's thinner by 4 times, the resistance should go up by 4 times, so times 4. And right now I have achieved 4R. The total resistance, the resistance is 4R now, but I need 4R to go to 2R. So in terms of the length, I have to make it shorter to reduce the resistance. So reduce by 2 times from 4R to 2R. So the length should be half. Therefore, the length, instead of the original L, it should be L over 2. So the answer is A. In this question, you are given 4 wires and they are all made of the same material connected in turns between the terminals P and Q over here. So which one will give you the largest current? So first of all, you have to understand that if you want the largest current, so the resistance has to be the minimum. Next, we can just use the basic concept. If I want the resistance to be minimum, so the length has to be the minimum and the cross-sectional area has to be the maximum. So this will achieve minimum resistance. So if you look at it, the length has to be the shortest, so it's 10 instead of 20, and the diameter has to be the greatest, the thickest. Therefore, the answer is B. So very straightforward. In this question, you are given the VI graph of 3 wires of equal length and same material, X, Y, and Z. The resistance and cross-sectional area are changing going from X to Z. So it's going in this way, okay, in that order. So which row describe these changes? Now, as you can recall from the previous chapter, current of electricity, all the three wires X, Y, and Z, they are ohmic conductor because the current passing through the conductor is directly proportional. That's why it's a straight line and it passes through origin. And another thing that you know, because it's a y-axis is the V and here's the current I, therefore you can find the resistance of the respective wire XYZ by just looking for the gradient, which is V over I, rise over run, which is basically the gradient. So if you understand that, because Z is the steepest, therefore the resistance of Z is the greatest, followed by your Y, and then followed by the resistance of your X. So in other words, from X to Z, so the resistance is increasing, and the cross-sectional area, because the resistance increases, the area, cross-sectional area has to be decreasing. So C will be the answer. In this question, you're given two scenarios, 1 and 2. And for the first scenario, the wire is 1 meter long and the resistance is 2 ohms. And when connected to a cell, and the cell, the so-called the EMF remains the same, the current in the wire is 3.0 ampere right now when the resistance is 2.01 meter. So now the second scenario is the same wire, that means same material, but now is instead of 1 meter, is 2 meters, okay, and it's the same cell. Now you can actually solve this easily because everything being the same, that means cross-sectional area, the material is the same. The only thing different is the length is double, so the resistance will be higher, which doubles also. So the resistance instead of 2, it will now be 4.0 ohms. Now, of course, the original, because the total resistance of the circuit is 2 ohms, the current is 3 ampere. But now the resistance is higher, double. So the current will not be the same, but rather it will be lower, it will be half. Therefore, it's 1.5. So using this reasoning, you can actually just get the answer very easily. The current is 1.5 and the resistance is 4 ohms. So the answer will be C. But of course, for those who wish to do by calculation just to be sure or just want to check, you can actually find the EMF. V equals to IR. The current is 3 and the resistance is 2. So the battery is 6 volt, which is the same for the second scenario also. So from your theory, you know that if the length of the resistance wire is double, the resistance will double also. So it's 4 ohms. So if you were to do the calculation of the current, I equals to V over R, the battery, the EMF is still the same, and now the resistance is 4, therefore you get a new current of only 1.5 ampere. So that's by calculation. In this question, you have bulb X and Y, okay, filament bulb, and they are of the same material, so usually it's tungsten wire. And the filament of lamp X is thicker, so the cross-sectional area is very big, so resistance will be low, and it's shorter than your Y, so the length is shorter, the resistance will be smaller. So from this sentence, you're able to conclude that the resistance of X is actually smaller, or rather your resistance of Y is bigger. So we have settled for the first part here, which one has a larger resistance, so the answer will be Y. Now next one, for which one will be brighter is a bit tricky here, but in general, brightness depends on power, and power equals to IV. Okay, so but in general, if you're able to prove either one, if the current is higher in lamp X, it will be brighter. If the potential difference across lamp X is higher, it will be brighter. So let's do a simple diagram here. Let's say this is bulb X and this is bulb Y. Now what is similar is the EMF here, the cell is the same, so no change. Okay, you can put in a value if you want to. So as we mentioned already, the resistance of X is actually smaller and the resistance of Y is actually much higher. Alright, maybe for easy reference, I'll just give an imaginary number. So this is 10 volt, and the resistance here, because it's smaller, let's give it 2 ohms, and the resistance of Y, let's give it a value 5 ohms. So the current, so I equals to V over R, the V is the same 10 and the resistance is 2. So that means to say the current flowing through the lamp X is 5 ampere. And the current flowing through the lamp Y will be V over R, 10 divided by 5, and the current is 2 ampere. Okay, so this will be very clear. So the current flowing through the bulb X is actually much higher compared to lamp Y, therefore it will be brighter. So it's X, so the answer will be B. So I hope with this video you are clearer with the factors that affect the resistance of a conductor. Alright, thank you.